The next part is talking about acceleration itself. That's a key part of the force, because force is mass times acceleration. So we'll end up with different ways of writing acceleration. So velocity. If our velocity is some function of displacement rather than time, this is the rule that is often quoted, but between you and me, I never use. The second derivative is d dx of a half v squared. Let's prove it. We know acceleration is the same as saying dv to t. Okay, we know that. Now, that formula is great if I want to link velocity and time together, which is what we've been doing so far. Then I'll make acceleration dv to t. But let's play with it. I'll rewrite it, implicit differentiation, chain rule, call it whatever you like, rates of change. dv dx times dx to t. Well, dx to t is velocity. So I could write it as dv dx times velocity. That formula there, v to v dx, is handy when we want to link velocity and displacement together. Okay, I'm going to rewrite v as d to v of a half v squared. So if you differentiate a half v squared with respect to v, you get v. But that now allows me to cancel the dv's, and there's the d dx of a half v squared. Also used when you want to link v and x. The difference is, I'll use d dx of a half v squared when I'm coming up with a indefinite integral, and I'll use v to v dx when I'm using a definite integral. And as you know, I prefer to use definite integrals, and that's why I always end up using v to v dx. Let's do a quick example here. We've been given an acceleration formula, it's in terms of x. And we want to find a formula for its velocity in terms of x, and they've given us some initial conditions. All right, let's see how we would use the d dx of a half v squared if we were doing it that way. If I integrate both sides, I'll end up with a half v squared is 3x minus x squared plus a constant. I would then sub in the initial conditions to work out what the constant is. And in this case, it turns out to be 0. Thus giving me a formula for v squared, but they want a formula for velocity, so best I can do at this stage is to simply say, well, it's plus or minus the square root of 6x minus 2x squared. Now, this is where some people get confused and they think, well, how can it have two velocities? And the reason it can have two velocities is there's no mention of time in this equation. It's linking displacement with velocity. So at one time I might be travelling to the left, but at another time I might be travelling to the right. I'm still at the same point, but just at different times. Here's how I'd do it. I'd do it as a definite integral. So I'd say v to v dx is 3 minus 2x squared. I would separate my variables, and I'll get the integral of v to v is the integral of 3 minus 2x. I know that when x is equal to 1, v is equal to 2. I'm trying to link x and v. And I'll do my two integrals. It naturally brings out the half v squared, because now I'm integrating v with respect to v, and I get half v squared. Sub in the v, sub in the 2 on the left-hand side, sub in the x, sub in the 1 on the right-hand side, play around with it, and we get the same equation. I just think a little bit more efficient and a little bit quicker. Some interesting things when we get it to this point, v squared, because v squared's got to be positive, so there's actually more information there. You see, because I could say, well, 6x minus 2x squared has to be greater than or equal to 0. If I solve that, I get x is always in between 0 and 3, and it now tells me something about the particle and where it travels. It's a very boring life this little particle has. It just moves between 0 and 3. That's all it does. It just goes between 0 and 3. There's nowhere else. Particle's acceleration, 3x squared. Again, they've given us some initial conditions. They want us to come up with the displacement equation in terms of time. Okay. I will start with v to v dx is 3x squared. Separate my variables. When x is 1, v is minus root 2. We want to find, first of all, a formula that links v and x together. Okay, a bit of integration. And I have v squared is 2x cubed. So v is plus or minus the square root of 2x cubed. But remember, we're trying to link displacement and time together. Well, velocity is dx to t. Now you'll notice I no longer have plus or minus. Because if I'm going to do calculus on this, I want a function. Plus or minus is not a function. Why did I choose minus and not plus? Because I've got to satisfy the initial conditions, because that's what I'm going to use to solve the problem. So when x is equal to 1, I have to get an answer of minus root 2. Therefore, I need to use minus the square root of 2x cubed, not plus the square root of 2x cubed. Putting that into index form, I get minus root 2x to the 3 on 2, separate my variables, and when t is 0, x is 1, let's find that equation that links t and x together. Bit of integration. You've got to love the integral from 0 to the value, because you know that, well, that's just going to be t in this case. Right hand side, add 1 to the power over the power. And I've eventually got a formula, but it's for t. I want x in terms of t. So I've got to make x the subject of all this. So t plus root t is root 2 on x. 2 on x is t plus root t squared. So I've got x equals 2 over t plus root 2 all squared. Let's have a look at an HSC one. Again, we've got a particle moving along the axis, nice and convenient. Got some initial conditions there. They're saying show that velocity is this, x squared plus 1. Okay. I have acceleration in terms of displacement. I want to find velocity and displacement, link them together. I'm going to use v to v dx. v to v dx is 2x cubed plus 2x. Separate my variables. When x is 2, velocity is 5. Okay, a bit of integration. You notice here, instead of going to half v squared, I just put the 2 on the other side straight away. Because I know I'm going to make v squared the subject, so let's put it over there straight away. So v squared minus 25 is that. Move the 25 over. V squared is x to the power of 4 plus 2x squared plus 1. Perfect square. X squared plus 1 squared. So v is x squared plus 1. Whoa, hang on. Why didn't I put plus or minus? I've got to justify it. So I'm doing a solution. I've got to let them know why I chose it, especially when they've said, show that. I've got to explain why I picked the plus and not the minus. So v has to be greater than 0, because I've got to satisfy those initial conditions. Hence, find an expression for x in terms of t. It's very similar to the last example. Well, dx to t then is x squared plus 1. Separate the variables. Right hand side, inverse tan function we'll get, won't we? Inverse tan of x, x on 2. There's t equals inverse tan of x minus inverse tan of 2. We're trying to make x the subject. So inverse tan of x is t plus inverse tan of 2. The tan of t plus inverse tan of 2. Mere mortal answer. We can do better than that. Tan plus tan on 1 minus tan tan. We get tan t plus 2 over 1 minus 2 tan t. All right. Whoa, that was a heck of a lot.